Welcome back. Today we're going to continue solving problems involving bending stress. So quick recap. Our equation is bending stress is a normal stress, that's tension or compression, and we calculate it using our internal bending moment times a y distance measured from the centroid divided by the moment of inertia of the entire area. So as an example, if we had a T-shaped cross section and we wanted to find the bending stress on that cross section caused by a bending moment, maybe the bending moment is this direction, the side that has the arrowhead on it from our bending moment is going to be our compression side of the beam. So we'll end up with compressive stress up here at the top of the beam. We'll end up with a tensile stress at the bottom of the beam, which will end up having to be bigger because the centroid of this T shape is going to be shifted toward the top. And how big our stress is depends on how far away we are from that centroidal axis. So the y distance that you might measure would be right there or right there. You're going either up or down a distance to figure out the stress. So our steps to solve are going to be step 1, find the centroid, unless it's a symmetric part where the centroid is right in the middle. Another step we're going to need to do is find the moment of inertia about the centroidal axis. So when we're finding that centroid, if here's our shape and we're finding that centroid, we want the moment of inertia about that centroidal axis. That is really important. So you're going to have to use, in most cases, the parallel axis theorem to find that. Oftentimes for this T, for example, you'd use the fact that the moment of inertia for a rectangle is 1/12 BH cubed, but then we have to add to it AD squared, which is the distance from the rectangle centroid to the overall centroid. Distance from the rectangle centroid to the overall centroid. So we're talking from this to this. There would be an example of a D that would go in here for D squared. So we find the centroid. Once we find the moment of inertia, then we can figure out how far from that centroid we are. We can figure out our moment of inertia, and we can plug in our bending moment and solve. So let's do one more example like we did last time that has a composite shape. We're going to have to find the centroid. It has a bending moment being applied to it, and we need to find the max compressive stress and the max tension stress, but we are just directly given the moment. We don't have to go and do any work to find it. Our governing equation we're going to use is sigma is plus or minus my over I. To find that centroid, that's our first step. I want to break my T shape up into two simple shapes. I think these two rectangles are the simplest. I like to color code these. Do whatever works best for you to find this, but our centroid location, the equation is we're going to add up the centroids of all the little shapes times their area divided by all of the areas. And I like to just do this in one equation, but if you'd like to build a table to do it, it will work just as well. So for the pink rectangle, my area is going to be 20 millimeters by 90 millimeters. So I'll just put that in the bottom and in the top, same area both places. But now I also need to multiply by the centroid location of that pink rectangle. So for this, I really would benefit from having a reference axis. And so I'm measuring my centroid down from the reference axis since the whole thing is 20 millimeters high. Its centroid is 10 millimeters away from my reference axis. Then we're going to add to this the stuff from the green. Green rectangle has an area of, it looks like it's 30 by 40 millimeters. So let's put that in the bottom and on the top of the fraction, leaving some space for the centroid location for that green rectangle. Its centroid is going to be right in the middle of the shape, and I need to find out how far is that from that reference axis. So the whole rectangle is 40 millimeters high, which means it is 20 millimeters from that edge, also 20 millimeters from the bottom edge, but I want to measure it all the way up to my reference axis. So since here's 20, here's another 20, it's going to be 40 millimeters away from the top. You run that through your calculator and you get an answer for y bar. It comes out to be 22 millimeters. And this is measured from the top. That is important. And which surface it's measured from is going to be important later on in figuring out max tension and max compression. So we've got the centroid. Let's do the moment of inertia about that centroidal x prime axis, if you want to call it that. Our equation, we just did. The equation is right up here. 1/12 BH cubed for each rectangle plus AD squared for each rectangle. So let's do the red ones first. The red one, I will have 1/12 the base is 90 millimeters and the height is 20 millimeters, which gets cubed. Then I need to add to it the area, 20 times 90 times the distance squared. Now I need the distance between the centroid of the pink rectangle and the centroid of the whole shape, which is 22 millimeters from the top. I think the easy way to do this is take the 10 millimeters we used before and subtract it from the 22 millimeters that we got. So do 22 millimeters minus 10 millimeters is your distance. It's the distance between the two centroids. We square that, have to square it so that we end up with millimeters to the fourth in both terms. Green rectangle will be 1/12. The base this time is 30 millimeters and the height is 40 millimeters, which gets cubed. Add to it the area, 30 millimeters times 40 millimeters, and then the distance between their two centroids. So again, we're going to grab that 40 millimeters that we had before. That's where the centroid of the green rectangle is from our reference axis, and subtract from it the 22 millimeters that you have to come down to get to the center of the whole shape. So we're plugging in 40 millimeters minus 22 millimeters, and we're going to square that. Now we've carefully put all those numbers into a calculator, and what we get is 868 times 10 to the third millimeters to the fourth. And millimeters to the fourth may not be convenient later on, so let's convert that. It becomes 868 times 10 to the minus ninth meters to the fourth, because to convert from millimeters to the fourth to meters to the fourth, you have to divide by 1,000 4 times. So that changes your exponent from +3 to -9. Now we can do stress. Let's do max tensile stress. Remember, your maximum stress in a beam is always going to be at the top and bottom, and it's 0 at the centroid. So if we want max tensile stress, we need to find the tensile side of the beam. That's done by looking at the direction of the bending moment. And whichever side, remember, the bending moment is created by a pair of equal and opposite forces, a force on the bottom that's pushing in and a force on the top that's pushing out effectively. And so on the bottom, we're in compression for this bending moment. On the top, we're in tension. So at the top is where we're going to find our max tensile stress. Stress is going to be M times a y distance divided by I. Our moment is 3 kilonewton meters. Our y distance is the distance that we go from the centroid, 22 millimeters down, up to the very top. So to be 22 millimeters, let's put all of these things in regular meters though. So I'm going to call that 0.022 meters. And let's divide by our moment of inertia. 868 times 10 to the minus ninth meters to the fourth comes out to be 76,000, and this was kilonewtons per meter squared. So that's a kilopascal, or probably better to just call that 76 megapascals. Max compressive stress. Well, if the max tensile is at the top, the max compressive is at the bottom. So stress is going to be a negative this time because it's compression. My moment is still 3 kilonewton meters. My moment of inertia is still 868 times 10 to the minus ninth meters to the fourth, but my distance is different. Now I need to measure the distance from that centroid, 22 millimeters down, to the bottom of the shape, which would be 60 millimeters down. So if you can't do that in your head, just call it 060 meters minus 022 meters. Total height minus how far down the centroid is. And running that through the calculator, you get minus 131,300 kilonewtons per square meter. That's a kilopascal. So that would be minus 131 megapascals. And I do want you to have a negative sign for compressive stresses always, and a positive sign for tensile stresses always. It should make sense for this problem that the compressive stress is bigger, and that's because it's a farther distance from the centroid. This T shape, because of all this extra area here, it shifts the centroid up closer to the top surface. So that means you have a smaller stress here at the top than you do at the bottom. Next, let's take this one step further and solve a problem where we don't know the bending moment. We have to do some work to find it. So here's the example that I've picked out. It's a simply supported beam. It has a roller on one end and a pin on the other. It has distributed loads on each end over 8 feet with nothing in the middle, and the distributed loading is 5 kips per feet. That's the magnitude. It is a nice symmetric I-beam, and we're supposed to find the max stress anywhere in this beam. So all of our bending stress problems so far that we've done, We've just jumped straight to the cross section where you guys know by now the centroid's here in the middle, the max stress will be at the top and the bottom. And if it's a symmetric part and the centroid is really in the middle, you'll have the exact same stress magnitude at the top and the bottom. So that part we already know. It's going to be at the outermost edge of the cross section. What we don't know is where along this beam will the stress be max. We don't know how big the bending moment is. So we're going to have to back up and use our great shear force and bending moment diagram skills to find the max bending moment. First, we need to draw a free body diagram, and I need to find the reaction forces at the ends. I decided to call this point on the left end A and the point on the right end B. So that means at A, I've got an AY and an AX because it's a pin, and at B, I'll just have BY. And then those distributed loads, if I replace them with their equivalent, I've got 5 kips per foot acting over 8 feet, so that 5 times 8 is 40 kips. And then the other distributed load will also have an overall effective point force of 40 kips. We can sum forces in the X first and find that AX is 0. Let's just sum moments. Moments about A equals 0. So the forces at A don't cause a moment. The 40 kip force is going to cause a clockwise moment. So we'll call that minus 40 kips. It acts at the middle of this rectangle. So it's 4 feet away from point A. Then we'll also have another 40 kip that will also cause a clockwise moment about point A. And its distance away would be 8 feet plus 8 feet, 16 plus 4 more. So it should be 20 feet away. And finally, to counteract those, I'm going to have a counterclockwise moment caused by BY, and its distance away should be 24 feet. Those all have to sum to 0. And so we solve for BY. BY comes out to be 40 kips. And then by summing forces in the Y direction, you will find that AY is also 40 kips. Nice symmetric beam, same load on each end. So now that we have found all of our reactions, we can do our shear diagram. Then we'll do our bending moment diagram. For our shear diagram, the first thing that happens, we would start at 0, but then we have an upward 40 kip point load. So we're going to jump from 0 up to 40 kips. And then what happens immediately, there's a constant distributed load with a magnitude of 5 kips per foot is pointing downward. So we're going to go downhill with a slope of 5 kips per foot. We're going to keep doing that for 8 feet. So I think we'll end up at 0. We'll double check that in a second. Our slope right here is 5 kips per foot. If you want to call that a minus 5 kips per foot because it's going downhill, that's fine. To find out how far down you're going to go, you would find the area under this curve. We already did that. The area under that curve is 40 kips. We were at plus 40. We went down 40. We should end up at 0. Then we have a nice long section of the beam with no distributed load. So we will have no slope for 8 feet. And then we start heading down again at that same minus 5 kip per foot. And at the end of the beam, we should jump up 40. It should look something like that, ending up at minus 40 kips, because this is also going to be minus 5 kips per foot. And the area under this other distributed load curve was also 40 kips. So you end up down at minus 40, and then the BY brings you back up to 0. So let me shade these guys in. Here's area 1. I might use that in a minute. So let's go ahead and calculate it. Area 1 is area of a triangle. 1/2. One of the sides of the triangle is 40 kips. The other side is 8 feet. That comes out to be 160 kip feet. And area 2 is exactly the same thing, 160 kip feet. Now we are ready to plot this bending moment diagram. We have no couples anywhere on here, so our moment diagram will not have any jumps, so it's got to start at 0. And it starts out with a giant positive slope of 40, and it's going to be gradually decreasing down to 0. So we start with a big slope, and right here we're going to have a 0 slope. So that's going to be a parabola, concave down because V is decreasing. And guess how high it's going to reach? We just found that value. It's going to reach 160 kip foot. Then what happens? We have no shear force, which means we're going to have 0 slope. So we're going to stay 0 slope for 8 feet. And then we're going to start going down. We're going to end up with a negative slope that starts at 0 and gradually becomes more and more negative. With another concave down parabola, the slope at the end should be minus 40, just like how the slope at the beginning should have been plus 40. And this is a pattern you should expect when you have a symmetric, simply supported beam like this. Your V diagram ends up being kind of anti-symmetric, and then your M diagram is symmetric again. If you'd like to shade this in to make it colorful, that's totally fine, but all we actually need from this diagram is to recognize that M max is 160 kip feet. Where it's that value is useful too, partially. It's going to be that value in this entire middle section of the beam. So if you are going to look for failure in this beam, it's going to be right in there, which I think is kind of interesting and maybe really counterintuitive because there's actually no loading here. But that is where the bending moment is biggest. That is where you would expect failure to occur. So we have M max. We're going to use that in just a second. Let's look at our cross section. It was 8-inch by 0.3-inch rectangle. In the middle, it was 10 inches by also 0.3 inches. And in the bottom, we've got another 8 inches by 0.3 inches. The top and bottom ones, they're identical, so we'll make them both the same color and maybe make this a nice orange in the middle. Because this is symmetric, we don't have to find the centroid. The centroid is in the middle, right here in the middle. So that's nice, it saves us some time. We can directly go to calculating our moment of inertia. It's the moment of inertia about that centroidal axis. So using my orange rectangle first, I need 1/12. The base is 0.3 inches and the height is 10 inches cubed. Remembering that the side that gets cubed is always perpendicular to your axis. So if your axis is this way, you're cubing the 10 inches. Then we need to add to it its area, 0.3 inches times 10 inches, times the distance between the centroid of the orange rectangle and the centroid of the whole shape. Look at that, is 0. This is equal to 0 because you don't actually need to use the parallel axis theorem when the centroids line up. But then we're going to add 2 of these green rectangles. They each have a 1/12. Their base is 8 inches and they have a little height. 0.3 inches is what gets cubed. So that'd be a little tiny moment of inertia by itself. What makes it have a big moment of inertia or a big contribution is this parallel axis theorem part. The area is 8 inches times 0.3 inches. And now the distance away, this takes some thinking. The centroid was at the middle. How far away is that centroid? Well, you need to come up 5 inches to get to the beginning of the green rectangle and then half of the height, so half of 0.3. So my total distance would be 5.15 inches, which gets squared. That is the number that so many students mess up. So look at the picture. If you need to draw out all these different lines to remind yourself you're going up 5 inches plus another half of 0.3. 5.15 inches. Altogether, this comes out to be 152.34 inches to the fourth. Now we can find the max stress. The equation is the magnitude of M max, the biggest Y value, divided by that moment of inertia we found. So our max moment was 160 kip feet. We found our max moment from our shear moment diagrams. So we put that into our equation, and then Y max, that's going to be the distance from the centroid to either the top or the bottom, since they're the same distance away. So I've got to go 5 inches up to get through the half of the orange rectangle plus another 0.3 to get to the top. So I will have 5.3 inches to get to the top. Oh, hold on, before I do that, why don't we convert feet to inches? Otherwise, we're going to have a really bad mismatch of units. So there are 12 inches in 1 foot. So that's a version of 1 that if I multiply by, it will cancel out the feet. Dealt with that, and then moment of inertia is 152.34 inches to the fourth. Let's multiply that all out. We get 66.8. I had kips for my force unit in here. I had square inches on the top divided by inches to the fourth. So I will have kips per square inch, which we oftentimes call KSI. And this doesn't really have a plus or minus with it. We were finding the overall max stress. So we found that the magnitude of the max bending moment, the distance to either the top or bottom, depending on whether you're at the top or bottom, will determine whether it's tension or compression. Let's figure that out, actually. This is a positive bending moment. Positive bending moment means that if I take my cut edge and I draw the moment on it, positive looks like this. So positive bending moment will always have compression at the top and tension at the bottom. The magnitude, though, of that stress at the top and the bottom will be 66.8 KSI. Couple of quick concept questions. Here's another symmetric beam, pair of 25 kip forces acting on it, perfectly symmetric. So what's the reaction force at A going to be? Well, if you can't tell it's symmetric, you can always do a free body diagram. The free body diagram will have our 2 downward 25 kip loads. At A, we'll have an AY, technically an AX, although it's probably equal to 0. and a dy. Yeah, something forces in the x direction, ax is 0. And equilibrium would give me that the sum of all the moments about any point we want, like point D, is going to be 0. So I would have, in a counterclockwise sense, 25 kips times 20 inches plus 25 kips times 20 plus 60 is 80 inches minus ay times, the whole thing is 100 inches. Ay is 25 kips. Y is also 25 kips. Next question, what will the shear force diagram look like? First, you're going to jump up to 25 kips. Then we've got no distributed load, so no slope. Then we go down 25 kips to 0. And we have no distributed load, so we stay perfectly flat. Then we go down 25 kips again. So we'll be at minus 25 kips. We have no slope because we have no distributed load. And then at the end of the beam, we go back up 25 kips. There is my shear force diagram. 0 slope everywhere because there's no distributed load with some jumps of 25 kips. What will the moment diagram look like? Remember, it was a symmetric beam, so it should end up being symmetric. We're going to start with a constant upward slope of 25 kips. Then we have no slope for most of the beam. Then we're going to have a downward slope of 25 kips. So that's what it's going to look like. What really matters is the max bending moment. So let's figure out how big it is by calculating area 1. That's 25 kips times 20 inches. Multiplying that out, 500 kip inches. So M max is 500 kip inches. There is, kind of going back to basics, what our first steps for this problem would be. We'd want a free body diagram. We figure out what the shear force diagram looks like. We figure out what the bending moment diagram looks like and find that maximum bending moment. So the next steps in the problem would be practicing what we've done today. We'd need to find the centroid of this shape. Since it's not symmetric, it'll be a little bit above the middle. We'll need to find the moment of inertia of that shape. And then to find maximum compression and tension, we would need to take the distance from the centroid to either the top or the bottom, multiply it by this maximum bending moment, and divide by that moment of inertia, and we could find the bending stress. All right, that's it for today. Thanks for watching, and we'll see you next time.